Momentum and energy, revision lesson. This is just an overview. So, momentum has to do with the quantity of motion of an object. The formula for momentum is P equals m times v, where little p is the unit for momentum, is the symbol for momentum, and the unit is kilogram meters per second. Now, in order to calculate the change in momentum, it's always the final momentum minus initial momentum. Now, because momentum is a vector quantity, we need to do this subtraction using vector subtraction. So what we do is it's PF plus PI in the opposite direction. So just make sure you're flipping that one, the initial momentum. So it's called adding the opposite. Now, whenever there's a change in momentum, it's usually caused about by an unbalanced force, which could cause a change in speed or a change in direction. And this unbalanced force acts for a short amount of time, and this is called impulse. So force multiplied by time gives you change in momentum, and there's many variations of this formula. So force multiplied by time is Pf minus Pi, but momentum is mass times velocity, so it can be calculated using mass times final velocity minus mass times initial velocity. But again, remember, directions are important for all this. And you can also calculate change in momentum by looking at the area under the force time graph. Now, this graph could have any sort of shape. It could even be like a rectangle, or it could be a triangle. So the formula for the area depends on the shape over there. Okay, now conservation of change in momentum. Now we use this concept when in order to reduce damage which is caused by impact. So this is how you pull back your hand when you're trying to hold a ball that's coming to you, or that is why we have airbags in cars. So how do you answer a question like this? The important thing to remember is that you got to remember that the change in momentum is the same. So it doesn't matter how something comes to a stop. It is when something's moving, it has momentum. When something comes to a stop, the momentum reduces to zero. So the change in momentum is the same. However, if you lengthen the time which it takes to come to a stop, because that's the same, your force is reduced. So that's what. And if the force is reduced, that's the force of impact decreases, then there is less damage. Okay, moving on to conservation of momentum. You use this for collisions and explosions, and there is a condition, and the condition is there should be no external force. An external force could be gravity, friction, acceleration, braking, anything. Okay, so if there's no external force, then we say it's in a closed system. A closed system is one there's no external force. And so how do you apply this? This is the sum of the initial momentum equals sum of the final momentum. This sigma is a Greek letter which means total. Okay, and it's quite nice if you draw a diagram to solve these problems. And again, remember, momentum is a vector, so take directions into consideration. Moving on to types of collisions, there are two types. There's one that's called elastic and the other one's called inelastic collision. So how do you know which one's elastic and which one's inelastic? The only way to find out is not by looking at their total momentum. If there's no external force, the total momentum will be the same for elastic or inelastic. But what's going to be different is the total kinetic energy before collision should be the same as the kinetic energy after collision. And if that's the same, then it's an elastic collision. However, in most cases, some energy is always lost in the form of heat because of the force of friction. And so the total kinetic energy at the start will be different from the total kinetic energy at the bottom, at the end. However, you need to make sure, you need to understand that the total energy stays the same. It's only that some of the kinetic energy has been changed to a different form. Okay, moving on to energy now. Law of conservation of energy says that energy can neither be created nor destroyed. It's only changed from one form to the other. So if something's at a height, it's got gravitational potential energy. When it falls down, that energy is changed to kinetic energy. And if no energy is lost in the form of heat due to friction, then we say that the gravitational potential energy lost when it falls down is all changed to kinetic energy. And using these equations, you can find out what speed does something hit the ground with. Then, in order to change energy from one form to the other, we need to do work, and the amount of work done is equal to energy changed. So if no work is done, then no energy has been changed. Or if no energy has been changed, then no work is done, vice versa. And they're both measured in joules, and 1 kilojoule is 1,000 joules. Moving on to power, it's how quickly energy is spent or how quickly work is done. Lots of formulae for power. It's energy over time or work done over time. And I've just expanded this. Work is force times distance over time. But you know, distance over time is speed. So power is also force times speed. So you can even do that. Okay. Elastic potential energy, this has to do with springs. Stretched or compressed springs store elastic potential energy. And Hooke's law has to do with when you stretch or compress a spring, the force is proportional to the extension. And a force extension graph is a straight line through the origin telling you force is proportional to extension. The gradient of this graph gives you spring constant, or that's a proportionality constant, and it tells you about the stretchiness of a spring. So the steeper something is, the stiffer the spring is, and the bigger the spring constant. Okay, and then the area under the force extension graphs gives you the elastic potential energy stored. It's also the work done in stretching a spring. Okay, this is not a constant force, it's an increasing force. So the more the force you apply, the more it will stretch and more the energy stored. And so the two possible formula, so the area under this is half fx, but because f is equal to kx, the formula on your formula sheet is half kx squared. Now also one other thing to draw your attention to, this formula f equals kx has a negative sign on your formula sheet. That shouldn't worry you. It just tells you if you pull a spring down, when you release it, it'll go back up. So it's just telling you it's going in the opposite direction.